All right. Okay. We're gonna start a lecture. Can you hear me? Okay. Okay. Yeah. Okay. Yeah. We're gonna start a lecture. Okay. Okay. Um. Yeah. In the last class, we wrap it up actually the Nyquist stability criteria. Okay. And so yeah, this is the example that I presented. And so to show you how the Nyquist stability criterion, right? Okay, to be applied. Okay. Oh, okay. I need to share the notes. Okay. Okay. I need to share this one. Share the notes. Okay. Yeah. Yeah. This is the example that we talked about at the end of the last class, right? Okay. So so basically, I show you that the different ways to apply the Nyquist stability criterion and the Rose-Hurwitz criterion. Okay. Okay. And so so you understand that the Rose-Hurwitz criterion is applied to the closed loop system. Okay. And not the open loop system, right? Okay. So in order to determine the stability of the closed loop system, okay, so you need a closed loop systems information to apply the Rose-Hurwitz criterion, okay, to apply the Rose-Hurwitz criterion. But for the Nyquist stability criterion, you only need the open loop systems information and draw the plot, right? Okay, so that's the difference between the Nyquist stability criterion and the Rose-Hurwitz stability criterion. I mean, Rose-Hurwitz criterion, we won't call it stability criterion. We just call it a criterion to decide the polynomial equation, the roots, the location, right? Okay, not like the Nyquist stability criterion, because Nyquist stability criterion was specifically developed for the control system. But the Rose-Hurwitz criterion, actually, initially, it was not intended for the control system. It was just a math, theorem. Okay, it's a mathematical results. Okay, so we just find out, realize that it can be applied to address the control system issues. Okay, so I think that from this example, you should be clear about the applicability of these two different stability criteria. Okay, and also you need to know when you can use Nyquist stability criterion and when you can use Rose-Hurwitz criterion. Okay, so I think that is the purpose for me to spend so much time to talk about this example. Also, in this example, I show you that how the stability margin actually can be calculated. Okay, not read it from the graph. Okay, so you can read it from graph, but the stability margins can be also calculated out. Okay, so if you know the open loop transfer function model. Okay, so that's so this example's information is very rich. So you need to spend more time to go through this example and to get to the points. Okay. Now the last things I want to talk about the Nyquist stability criterion before I move to the control design. Okay, so it's this. Because when we define the both phase margin and the gain margin, and you might realize that, oh yeah, they are separate. But even if we define it separately, okay, and it's an evaluation of the gain situation and the phase situation, okay. But in practice, they are used. They have to be applied jointly. What does this mean is that do not think that a system that has a big gain margin but has a very little phase margin is going to be good. Vice versa, you think that a system has big phase margin but without have any gain margin is good? No. Okay. No. Okay. In practice, you need to have both margins reasonable, same time. See, in this figure, it shows clearly. Okay. See, look at this. The right figure first. The right figure shows what? You can see that the figures on the right, and if you look at the gain margin, because you see the intersection between the Nyquist plot and the real axis, it's at what? It's at the origin. So you can, based on the definition of the gain margin, in this situation, your gain margin is what? It's infinity. Your gain margin is actually infinity. Okay? Why? Because it's zero. Okay? Denominator is zero. Okay? So your gain margin is infinity. Okay? Now, what does this mean is that this system, if you use it to construct the feedback system, G of S here, and you apply the gain here, this gain could be any positive number to infinity, and the closed loop system will still be stable. Okay, so you have a huge gain margin. However, if you look at the phase margin, you can see that this is the first intersection between the Nyquist plot and the unit circle. So you're using this crossover point to find out the phase margin is here. You can see that the phase margin is very small. So this kind of a system, it could be also vulnerable, okay? Vulnerable to a small perturbation, okay? Vulnerable, fragile, okay? Maybe a small perturbation to perturb the phase, and the system will become unstable because the phase margin is too small. So if you look at the gain margin only, you might think the system is very stable, okay? But unfortunately, this system is not, okay? It could be easily perturbed into the unstable zone because the phase margin is small. The figure on the left is on the opposite case, okay? Opposite situation, okay? See, in this case, you do have a big phase margin. If you draw a unit circle here, okay? So the first intersection is here. So the phase margin, yeah, it's pretty good. But this system, this system has a very little, gain margin. Because you see, say if a -1 here, if the -1 0 point is here, then you can see that if you just increase the gain a little bit, and the encirclement will happen. So if the encirclement happens, the system becomes unstable. So the figure on the left shows the opposite situation. It's that you have a big phase margin, but you have a very small gain margin, which is also not good. Okay, which is also not good. Okay, so these are the two situations that you have one margin is big and the other margin is small. And practically this kind of system, we treat both of them very vulnerable system, not a good stable system. In order to have a good stability, okay, measure, and you need to have both margin to be big same time, to be reasonably big same time, right? Okay, to be reasonably big same time. For example, like this one, you see, like if you have a plot, like this, okay, see, gate margin is here, reasonably big, phase margin is here, also reasonably big, okay? So this will be a good better system, okay, in terms of the stability margin, okay, in terms of the stability, okay? So this is something that I want to make it clear, okay? Okay, do not take the margin separately, okay? Take both of them same time, okay? Consider both of them same time. Okay, so yeah, that's pretty much about the Nyquist stability criterion. So now we're going to move to the design part, the design, control design in frequency response, okay? Control design in frequency response, okay? So yeah, let me share another lecture. Okay, yeah. So design of controllers with frequency response, okay, with frequency response. Now in this part we have two problems to address. First problem is that yeah, we need to find out the performance analysis with the frequency response, okay? Okay, yeah, we need to know how we can evaluate a system is good or bad. And if it is not good, yeah, it's always like that. You see, we talk about this in the control one all the time, right? So what is the function of a control? What is the point to add a control, right? The point to add a control is that you are not satisfied, you're not happy with the plant, design itself. So you try to add an extra device in your hand, designed by you, to make the plant, the target system, operating better, right? So first thing we need to talk about is the performance analysis. This is characterized with the frequency response. Remember, in the control one, we talk about the stability performance, we talk about tracking performance, we talk about the transient performance, but most of them, are characterized on the, not using the frequency response, right? Okay, for example, like the transient, performance, we are basically characterized the performance index on the what? On the unit step response, right? On the unit step response. So we need to talk about that. How the performance analysis could be conducted with the frequency response. Now then, we're going to move to the control design, okay? So that is the contents here. Okay, so now performance analysis. So yeah, don't forget it. You see, from the Nyquist stability criterion, we already find out that, okay, yeah, the Nyquist, the major question here is this, okay? Major question here is this, okay? Is that, okay, if you look at this figure, if you know the G of S, well, assume that H of S is equal to 1, okay? Well, we don't consider the sensing, model again, okay? Okay, so the question here can be very well demonstrated in this two transfer function. One is the G of S, which is the open loop system. When we take the H of S is equal to 1, okay? And then we have a closed loop system. Yeah, if you take a H of S equal to 1, then this one is going to be just the G of S over 1 plus G of S, right? Okay, so you're going to have a closed loop system transfer function. You're going to have an open loop transfer function. Okay, so when we talk about the performance analysis, what we want to do is that, okay, I only want to use the information of the G of S, and then I'm going to predict what kind of performance the closed loop system is going to be. Okay, right? Okay, see, the first one I've just mentioned, you know, the Nyquist stability criterion. My Nyquist stability criterion is such kind of performance characterization, okay? Because it uses, utilize the open loop system's Nyquist plot and utilize the open loop system's pole information to predict what's going to happen for the G sub C of S, the closed loop transfer function stability, right? And you can understand that Rose-Hurwitz criterion is not such kind of, does not satisfy this kind of expectation, okay? You can, in other words, if you only have the information of a G of S, you cannot use the Rose-Hurwitz criterion to predict what happens for the closed loop, for the G sub C. So Rose-Hurwitz criterion does not satisfy our expectation that is showing in this relation, okay? Okay, so yeah, it is clear that in frequency response, we're going to be always stick with the Nyquist stability criteria. Okay. Okay. Now let's look at the other tracking performance, which is the tracking. And this performance we talk about, we spend a lot of time in control one, right? So yeah, this is a good opportunity to review it again. Okay, to review it again. I just want to show you one more time because actually I remember I mentioned this in the control one a little bit, just a little bit. Okay, maybe you did not understand the point there very well. Okay, but here I'm gonna highlight the relation, then especially highlight this relation here. I'm gonna erase this. Okay. Highlighted this relation here, then you're going to understand the tracking performance. Wow, we actually have already done this, but it's just we did not realize it, right? Okay, so now if you recall, the tracking performance is very well characterized by the open loop transfer function G of S, right? Okay, again. You don't need me to mention this again, okay? H of S is always equal to 1, okay? Okay, it's very well characterized by the transfer function of the G of S. Remember, in order to evaluate the tracking performance, which is basically, we use the error function signal. We use this error signal to find out what is going to be the tracking, right? Okay, so yeah, remember, we need to reorganize the open loop transfer function into this kind of expression, right? Okay. See, specifically, I don't care about this part because this part, let me give it a G prime of S. And we know that this one must satisfy a condition that is the G prime 0 equal to 1. Is that right? Okay. So what we are concerned about in terms of the tracking performance is exactly this K over S to the power of N, right? And specifically, we know that this N, if you recall, what do we call this N as? It's the type of the system, right? It's the type of the system. It depends on how many integrator the open loop system will include, right? Okay, then we classify the open loop system into type 0, no integrator, type 1, and the type 2. 1 integrator, 2 integrator, and blah, blah, blah. You can keep going, okay? You can, just keep this, types, going. Okay. Okay. Then in order to evaluate, this is the tracking performance that we needed. Of course, if you remember, I said it many times, before you go for this table to evaluate the tracking performance, what you need to do? Before you evaluate this table, the tracking performance, what you need to do? Someone? Let me see. Check the stability. Yes, Zia, yeah, you are good. Okay, I'm glad that you can still remember it. Okay, Iman, find the type is straightforward. Check the stability. That is very important because you can see that from this. Let me erase that. You see, the tracking performance is first is that because tracking performance, like what I said, you need to evaluate the signal, the error signal E of S. So this transfer function from R to the E is well characterized in this transfer function. Assuming H of S is equal to 1, then your transfer function is actually 1 plus of S, G of S, right? 1 over 1 plus G of S. And this is actually the closed loop, okay? This is also the closed loop transfer function. This is the transfer function from R to E. So you know that as long as you are involving the closed loop system here, you have to make sure the closed loop system is stable, right? So even if I did not ask you to do that, okay, this will also apply to the future examination problems. Anytime, okay, you have to have this kind of a sense that you need to make sure this closed loop transfer function is stable. Specifically, you need to check the denominator of the transfer function to see where the pole is going to be, okay? Before you move to apply the open loop information to find out the tracking, okay? Okay? Don't take it as granted, okay? Don't just drag open loop system and say, hey, yeah, I got the tracking performance. If you don't check the closed loop stability, that there's pretty much a chance that you drag a transfer function here for the open loop, and the closed loop system is not stable. If the closed loop system is not stable, you know what? You can see this is the evaluation of the error signal, right? Then this signal is going to go to infinity. Then this table is wrong, okay? This table is wrong, okay? In other words, this table implies that the closed loop system must be stable, okay? So I emphasize this one more time, okay? So you got to have this kind of a sense. Okay, so if the closed loop system stability is guaranteed, and then the problem actually becomes very simple, okay? Yes. What question? What do you mean? What do you mean given? I don't understand the question, okay? But let's not talk about that at this moment, okay? Okay. Yeah. So, and then you can see that this table, you can see every entry here only involves the K, okay? So, in other words, as long as you know what kind of a system you have and what signals you are going to test, and the error signal, the steady state error signal, okay, the steady state value of the error signal can be read out from these entries, okay? See, let me just simply repeat that, okay? For example, if you have a type 0 system, which means that you don't have any integrator here, and then you know that the type 0 system and can only reasonably track a unit step signal and with an error. In this case, the type 0 system's error is 1 over 1 plus Kp. The Kp is equal to K, okay? The Kp is equal to K, right? Okay. So the type 0 system can be used to track a step signal, but with error. Not perfect, but with a bounded error. Okay? But if you want to use a type 0 system to track a ramp signal, not possible, because the error is always infinity. Well, let alone the parabolic, the acceleration signal, right? Unit acceleration signal, you can't do it. Okay? Okay? So for a type 1 system, yeah, the type 1 system actually can track the unit step signal perfectly, so the error is 0. However, it will track a unit ramp signal with error, and the error is bounded by the 1 over kV. Again, this kV here is equal to k. So you can read this error from the value of k. Okay, from the value of k. Okay, from the value of k, right? Now, can you use a type 1 system, with one integrator? Okay, the open loop system has one integrator, and to track a acceleration signal? No way. The error is infinity. Okay, no way, right? Okay. Okay. Now, type 2, yes, you can track the unit step, unit ramp, unit step, and the unit ramp, signals perfectly, with the error is 0. But you're gonna track the acceleration signal with an error. Okay, acceleration signal with an error, and the error is bounded by this number. Again, this k sub a is equal to k. Okay, so once you know the type, read this number n, and then specify what kind of signals you want to track, and the tracking performance can be very well read from the value of k. Yeah, this basically means that you're gonna as long as you know the open loop system's information, then you pretty much know the tracking performance of this closed loop system. Okay, right? Okay, and you might want to say, oh yeah, you need to check the closed loop system stability, so you still need the closed loop system's information. Is that question valid? Is that a good question? Can someone tell me? Do you need a closed loop, transfer functions information to tell the stability? No, right? Yeah. Well, you can. What do you mean by you can use other method? What method? Yeah. Well, you see, apparently, because here the open loop transfer functions information, so you can definitely apply the Nyquist stability criterion to address this closed loop system stability. It's the same, right? It's the same. Yeah, Nyquist, not rules. Okay, not rules. Rule is criterion, right? Okay, it's the same. You see, you want to evaluate the stability of this transfer function. It's the same. Okay, it's the same. Okay. It doesn't matter what kind of numerator is going to be. The Nyquist stability criterion just evaluate if the closed loop system, the denominator is stable now, right? Okay. So so I just want to say that with the information of open loop system, you can check both the stability and the tracking performance, no problem. And on the application order, you have to apply the Nyquist stability criterion to check the stability, closed loop system stability first, and to make sure that for this kind of open loop transfer function, the closed loop system is stable. Then you can move to the evaluation of the tracking performance. You see what I mean? You cannot reverse the order, okay? You cannot reverse the order, okay? You have to check the stability first, and then make sure the tracking performance it's clear. Okay? It's any question? Any more question about this? Okay. So yeah, the next performance is transient. Okay, it's a transient. Okay, and so you can see that in the control one, we did define the transient performance for a first order system, for example, and the second order system, the next page, okay, in the next slide, right? And but don't forget it, we defined at that time, we defined the transient performance is based on the closed loop system, okay? It's based on the closed loop. You see, when we characterize a first order system in this one block, we imply this one block system is a closed loop system, okay? Okay? You know what? We always, post the performance requirement on the closed loop system, okay? And before you move to the control design, the reason that you evaluate the your plant's performance is just try to find out the deficiency, okay? Try to find out what is going to be the deficiency between the plant system itself and the target to the closed loop system, controlled system, right? Okay. Once you can identify the deficiency, then you will be able to find out the appropriate controller to be added in here to make sure the closed loop system satisfy your performance requirement. So in this sense, the performance requirement is always posted on the closed loop system. Okay, so now for the first order system, we know that the performance is actually very easy to be characterized. You see, you only need to know the time constant, which is equal to the 1/8, the closed loop, the poles. Okay, you see the poles of this transfer function, right? Okay, so if you know that, and then this transient performance is very well characterized, okay, because it's based on this time constant, right? Okay, so this is a first order system. So very easy to be characterized. One parameter, you're done. Okay, time constant. One parameter, you're done. Okay, now what about the second order system? Yeah, we know that. You see, we are using the standard second order system, right? Okay, we assume, well, basically you are evaluating, define the, this is your second order system. Okay, so yeah, you use a unit step signal here and check the unit step response. Evaluate the unit step response of this second order system. Okay, and then on this unit step response, we define the transient performance, and we know that actually this transient performance are very well characterized by two parameters. One is the damping ratio, the other one is the natural frequency, right? Okay, so that's what I mean here. That's what I mean here. The damping ratio zeta and the natural frequency omega n, they actually determines the transient performance. Why? Because you see the unit step response can be obtained in this expression, okay? And so yeah, if you take the derivative, yeah, you can, the transient performance index we propose is what? Rising time, the peak time, and the settling time, and the overshoot, you see, and the oscillation, okay, damped oscillation, right? Okay, frequency, damped oscillation frequency, right? So this transient performance, well, the transient performance you can find out, it's not easy. It cannot be characterized with one single index, okay? Because this transient performance is kind of complicated, okay? It's not straightforward. So that's why you need a multiple index to characterize transient performance, okay? You need to first you need to know how fast the response is going to be, which is characterized by the TR/TP and the settling time TS. How fast the response is going to be, okay? And this TR/TP and TS, they measure the the response time at a different stage, okay, right? See, the TR is measure the rising, stage, how fast the response is gonna keep rising, okay? The TP actually is pretty similar to the TR. They are actually kind of overlapped, okay, redundant, okay, because you see, if you have a fast TR, then your TP is gonna be fast, okay, for sure, okay. You won't see the response is gonna rising fast here and then all of a sudden flattened. No way. The physical system cannot do that, okay. This is what we call the physical system, okay. This is determined by the constraint by the law. So the natural law does not allow this kind of response happens unless there is a human being's interference, okay. Unless, for example, you force the system to stop, then of course, then the response is gonna stop, right? Unless human being you interfere with the system response by enforcing, for example, you turn off the system at this point, then of course the system is going to stop, right? So if you let the system operate itself, you won't see this kind of behavior. Instead, if you see the fast rising time, the peak time is also fast. So that is why, in this sense, the peak time and the rising time, they are sort of overlapped, okay, redundant, okay. But the settling time is another measure. This settling time measures what? Measures that when the response settled into a bound within a bound of the steady state value, okay, with the steady state value, right? See, so how the TS is gonna be? It will depends on the damping ratio. Okay, it will depends on the damping ratio, right? Okay, so this is measure the stage, when the signals almost settle, okay? Okay, now this overshoot, what? It's gonna be the measure, also measure the damping, okay? This overshoot, basically, we find out, this overshoot, can be calculated in this formula, right? We derive it, from this response expression, and we find out that actually this overshoot value is only related to the damping. Okay, can you see? You can see that, right? Okay, actually, you should be familiar with this formula. Okay, so the damping ratio here, and of course, we can characterize this as a omega d and sigma d, okay, with this, remember we have a way, this is just a computing, okay, this is just how we can compute this formulas with the deployment of the poles, okay, according to the position of the poles of the secondary system, okay. And so yeah, so this is pretty much, this is the TP, and this is the peak time, and the settling time, it can be estimated by this, and overshoot. So damping ratio actually is equal to the cosine theta, okay, right? So you can see this is a very well characterized transient performance by two parameters, zeta and omega r, and omega n, natural frequency. Okay, now here we introduce one more, performance index for the transient performance, which is what we call the bandwidth. Okay, the bandwidth actually is defined as a frequency when the magnitude of the transfer function dropped, about this is a 0.707, right? Square root of 2 over 2 is actually equal to the 0.707, right? So this means that